So this is an explicit solution, right? So this is y equals this.
You can plug this whole thing in for y then,
Okay.
but you need to take its first and second derivatives to plug it in. You just need a second.
Second, right?
Derivative is where you take the exponent and put it in front and then subtract. You take the power, move it to the front, and then subtract 1 from the power, or
Yeah.
then it'd be 2x plus x to the negative 2.
Okay. Yep.
From the second derivative, it'd then be 2 minus 2x negative cube.
Okay.
So you did plug that into the equation where it's the second derivative. So it'd be 2 minus 2x negative cube, and then minus 2 over x squared times,
Wait.
or x squared minus x to the negative 1.
Okay. Then what's going to happen?
Yeah, to distribute the 2 over x squared into the rest.
Okay.
It'd be, that just becomes 2 minus 2x negative 3 minus 2 plus, or just leave the myself.
Plus, yeah, we do that.
Plus 2x. Oh, because it's the negative in front of the exponent just means that it's like in the denominator, right?
Yeah, like negative exponents.
Like you can
Get it out of the denominator by
make this
making it negative exponent.
So it'd be plus 2x to negative 3 power.
Yeah. Yeah. And looks like that does work. So this is an explicit solution. Might not be the only one, but it is a solution to it. Okay.
Yeah.
All right. So what'd you do for this?
For this one, I got all stumped just because of the y square portion. Most of the other problems and the ones that I did in class didn't have it where the dependent variable was squared or anything.
Okay.
So I'm not really sure how to start with it.
Yeah. So remember in a function, if there's y's mixed in, do you know what you have to do to differentiate it or how to differentiate it? You want to treat the y as a function of x. Okay. So if y is a function and the squared's also a function, notice you have a function within a function, right? Or a composite function. So when you differentiate this, do you know what rule you have to apply?
Product chain rule.
Chain rule, right? Product rule is function times a function. Chain rules for a function within a function. Okay, so how would chain rule work here then?
It would be like, you do the outside first or the inside?
Yeah, I suggest outside first. So what's the outside function?
It'd be 2 times y or the function.
Yeah, two. The squared's the outer function, so you apply the derivative rule, which is to bring it down to, and then you still have the inner function of y that you maintain. Right, so the derivative is just 2y. And then what's the derivative of the inside function?
dy dx? Or?
Yeah, exactly. Y is the inside function, so its derivative is dy dx. Does that make sense? So that's called implicit differentiation, which is essentially just a chain rule. So anytime you have y's mixed into your function and you're trying to differentiate, you have to apply the chain rule, meaning that anytime that every y term that you're dealing with, you have to attach a dy dx to it when you're differentiating it due to chain rule. That makes sense.
Okay.
Okay, so then if you differentiate this expression or given equation, then what do you got?
2x plus 2y dy dx equals just 1
What's the derivative of 4?
or 0.
0. Yeah, it's a constant, right? Okay, then what next?
Subtract 2x from both sides.
Okay,
And
the
divide sides by 2y.
okay, and then what do you get for dy dx?
Yeah, dy dx equals negative x over 1.
Yeah. Okay, what does that tell you then?
It's not.
This function is not a solution to this differential equation. The solution is if you had a negative, x squared minus y squared would be a solution, but not x squared plus y squared.
Mhm.
Does that make sense?
Yeah.
Right, so this does not equal x over y, not solution. Do you remember how to differentiate this? Something like this?
You have to get the y by itself first.
You don't have to. You can differentiate implicitly. Do you remember how to do that?
No, I don't.
Okay, so what we can do is treat the y term as a function of x. Okay. So if we treat y as a function of x, and notice that here, since you're squaring the y, that means you got a function within a function. It means that you have to apply chain rule when dealing with any y terms. The idea here is that if you take the derivative of y squared, you apply the power rule. So that becomes 2y, but then y itself is a function. Chain rules applies when you're taking the derivative of a function within a function. So in this case, y squared, we treat y as a function of x. So since we're squaring it, you take the derivative of the outer function, which is 2 times 2y, but then you have to multiply by the derivative of the inner function. So the inner function is y of x. We use dy dx
Mm.
to represent the derivative of y. Does that make sense?
Oh, yeah, because it's derivative of y.
Yeah, so y is the inner function, the squared's the outer function. We're assuming that we could rewrite this as y equals, so that's why we treat y as a function. But we don't have to do that if we just use implicit differentiation. Okay, so we know the first term derivative of y squared is going to be 2y dy dx. What's
The derivative of the rest of the equation.
yeah, we're going term by term, right?
So then it'd be minus 3x squared. Or,
Okay,
and the 8 just goes away, right? It just equals 0.
okay. And then what can you do from here?
You can add 3x squared to the other side, or to both
Yeah,
sides.
yeah. And then what do you get after?
And then divide 2y by both sides. And you have dy dx.
Yeah, exactly. So we see that this, right, the derivative of this relation is 3x squared over 2y, which is X's differential equation. Okay, so do you know how to set this up?
No, not really. Just the e. I don't remember how to use e for when it's raised.
So if we look at the differential equation, what's something we have to figure out to plug in?
It's the derivative for
Yeah,
dy dx.
the derivative, right? First, we need to find dy dx. So how do we do that?
And then do we just move everything to the other side?
By just differentiating implicitly, like we did previously. So yeah, so we have to go term by term, right? So what's the derivative of x?
One.
Okay, what's the derivative of y?
Not the same. Or
Well, we're taking the derivative with respect to x. So you can treat y as a function of x. So what will we call it?
no more. By of x.
Yeah, dy dx. Derivative of y is dy dx.
Yeah. And then
Again, here you have to apply two multiple rules. Do you know which ones?
you just have to do with logs or something like that.
No, because logs is the inverse. That's for when you're solving exponential equations. Here we're just taking the derivative.
So you would be like a chain rule then?
Yeah, so there's going to be chain rule, right? Because it's not just e to the x, it's e to something, and a function that's plugged in. So what's the outer derivative?
To be x times y. So that's just y.
Well, do you remember what the
So
derivative of e to the x is?
they'll just use the x.
Yeah. So what's the outer derivative? What's the derivative of e to the x times y? Or the outer
E to
derivative,
the
right?
x.
Yeah, exactly the same. It's itself. Now we have to deal with the inner function, right? Which is x times y. You know what the derivative of that is?
Dy, right?
Uh,
Unless we write y as function still, or are we leaving it?
so here you have to treat x is a function of x. Y is also a function of x. So you have a function times a function.
Is that product rule?
Yeah, you have to apply product rule here.
Forgot how to do product rule.
Just remember, product rule is take the derivative of each times the other function and add them together. So what's the derivative of x?
It's just one.
Okay, 1 times y, right? The other function. And then you add, what's the derivative of y?
Of dy dx.
Yeah, and then multiply by x, right? So just alternate derivatives at the function. One derivative goes with the other function, alternate them, and then add them together. Okay.
Yeah.
Okay, so now what do we do from here?
What were we trying to solve for?
Our goal is to find the derivative. The goal is to solve for dy dx, because that's what we need to plug in to our differential equation. Notice that we've got multiple dy dx terms, right?
Right.
You know how to reduce it to one dy dx term?
I don't.
Okay, so let's do this then. What we want to do is get all the dy dx terms on one side and all the other terms on the other side. So how do we do that?
Right. We add or subtract one for both sides.
Okay, what else can we put?
We subtract y times e to the xy.
And what else
That
is
would
left?
leave you dy dx plus dy dx times x times e to the xy.
Okay. Okay, so do you know why we want the dy dx terms together?
Can you factor them out?
Yeah, factor, right? That's how you reduce it. Okay, and then what do you do from here?
You divide both sides by 1 plus e to the xy times x.
Yeah. Okay. All right, so now we have this our dy dx. What do we do with that?
Um, or we plug it into our equation.
Yeah.
We add
What's
before,
what's that look
or
like?
the ones they give.
Yeah, a
1 plus
differential equation.
x times e to the xy times this down here. So -1 minus
Yeah.
y times e to the xy over 1 plus e to the xy times x.
Yeah, yeah. What's gonna happen?
technically treat this all as one value and cancel out the denominator.
Yeah, denominators cancel out, and then what's going to happen with the numerators?
They cancel each other out.
Yeah, and you end up with 0, right?
Yeah.
You see how this, right? So this expression, right? It fits this differential equation, the solution to this differential equation.